joining this STRIDE UTC webinar titled Real-Time Database Decision Support System for Arterial Traffic Management. And this project was funded by STRIDE, Southeastern Transportation Research Innovation Development and Education Center, which is a USDOT center, regional center, one of the regional centers in the United States. It includes 10 universities as part of the consortium. This is a joint effort between UF and FIU team that we had on this project. So we're going to talk about the background of the project, the traffic responsive plan selection system in general, which is the basis for the system that we are developing, the goal and objectives of the project, talk about the newly developed strategy, which we call performance-based and proactive TRSP, project case studies, and the evaluation of the performance conclusions and recommendations. So the research team, as I mentioned, involved University of Florida and Florida International Universities, with myself, Dr. Lily, and Hector Mata and Hassan Amini, who did a big part of this work and as the research activities. In most cases, signals are controlled by time of day strategies, where the time that the signal change is fixed between days for the morning peak, midday peak, weekend peak, PM peak, and so on. And we know that this is not sufficient in a lot of cases. The reason is the variations day to day. For this reason, there has been a lot of interest since the 1980s also in adaptive signal control systems. And there many agencies started considering that and installing them. However, these type of systems are not for every location. They require a lot of resources, high cost, and technical resources to implement them. They're not a black box. They need the understanding and calibration of the system, and so on. And in addition, they would not work in all conditions. So, for example, if you have saturated conditions or condition where you have surges, maybe in traffic, those conditions, not all adaptive signal control system would work for. So for this reason, there have been not as big market penetration of those adaptive because of signal control, because of those high resources and high cost and so on. In recent years, data are becoming available from multiple sources, including the high resolution controller data, travel time, and emerging data collection technology that allow us to estimate a types of performance measures that we call automated traffic signal performance measures, which basically are used by the agency to assess the performance of their arterial systems. Given that this type of data is becoming available, and these type of performance measures are becoming available, that motivates this research project, in that these type of measures can be used to support signal control. So one would think that such measures can be used for both traffic adapt. In fact, even for time of day, they can be used for refining time of day plans, but they can also be used for traffic responsive plan selection, traffic adaptive plan selection, and so on. The TRPS, which is the traffic responsive plan selection, have been proposed since the 1980s and maybe the late 1970s, when the US DOT developed the UTCS system that continued to be implemented until the 1990s and early 2000s, or operational until that period of time. And then, however, even with those systems, closed loop systems have several type of TRPS and so on. However, this system has not been widely used due to issues, including the need for near-time prediction. A lot of time when you, by the way, those systems, they select the plans from pre-stored library of plans. So they look at what is the signature of the traffic today and what is the signature on plans, and they do matching between the two, and they select the closest plan from the library of plans. So there are several limitations that in those TRPS system is the need for near-time prediction. The reason for that is that by the time that the system determined that the traffic is going in a direction and select the plan, that traffic may change in the next 15-30 minutes, and then the plan selected may not be the most appropriate plan. There's also difficulty in the design of the stored plans. What are those best plans that can be used as part of the TRPS to be stored in that library? Also, there's a need to weight the detector data. If you have different detectors on the arterial and the cross street, main line on main street and cross street, you want to weigh those depending on the importance of them for identifying the signature. And also they need to set the plan activation thresholds. That can be difficult. Most of the time that is done based on judgment. There is a need for installing and maintaining additional detectors. That becomes less important because a lot of agencies are considering those detectors for ATSPM, and the need to limit the number of plan transfers, because the more transitions between a plan within a peak period, the more you're going to have a transition delay due to transition between the plans. So the project goal and objective is to develop this performance-based TRPS strategy based on the ATSPM measures as input. And that ATSPM strategy will require the development of methods to categorize the traffic patterns, considering the day-to-day variation, develop and assess a model for near-term prediction of traffic patterns to allow us to activate the plans based on near future prediction of the traffic patterns, and then finally utilize the categorization and prediction to develop the plan and also to activate the plan in real-time operation. The performance-based TRPS make use, as we said, of the ATSPM measures, and basically it uses in our case, we are using the k-means cluster analysis. And several of our previous work, we found that the k-means cluster analysis is although it's simpler than other type of clustering, it produces good results and maybe superior results compared to the other type of clustering techniques. So we use different kind of measures, including in the clustering, vehicle counts, travel time, green occupancy ratio, green time, and signal utilization ratio. And then the next step is to identification of signature day for each cluster to be used in optimizing the signal control for that cluster or that pattern. The following step is to develop the signal timing plan using an optimization tool to store those in the library of plans to select from. And finally, to develop a machine learning model to predict the traffic pattern, which are the clusters that we identify in the cluster analysis in real-time operation for the next 30 minutes for use in the plan activation. We investigated different machine learning predictive models, and we have these 7 type of machine learning. We investigate their performance based on what is used normally to in machine learning literature to compare those measures to those algorithms. And basically, as we're going to see in the evaluation, we found that the artificial neural network produced the best performance among these 7 algorithm or models that we use. Lily, do you want to?
Sure. Thank you, Mohammed. So this is the first case study that we began to work with. This is a corridor, Newberry Road, around I-75 in Gainesville. It included about 6 different intersections, and just to give you a sense of what's happening there, there is on the bottom side here, the south side, there is a major mall, and then the interchange with I-75. So it's a very busy corridor. It runs east-west. Toward the east is where the University of Florida is. So this is a very heavily traveled corridor. And we had already tried to optimize this with adaptive signal control. And one of the issues is that there's so many driveways in between the signals that it's really difficult to predict what's happening from one intersection to the next. So we really wanted to see how this corridor would perform with this with the cluster analysis and optimization. Next. However, major issues with the corridor. First, there were lots of missing data. And so it's really difficult. It was really difficult to identify clusters that had kind of uniform characteristics. So the number of usable days was relatively small, and so we were not able to identify suitable clusters. It ended up being just a couple of clusters, and it was not. We ended up not being able to use this. There were lots of different issues also with matching the volumes with the travel times. And so again, in terms of lessons learned for applying this type of methodology, you need to have a complete set of data for hopefully for a year so that clusters can be identified. And so missing data can really affect the results. Back to you, Mohammed.
Okay, thank you, Lily. Given all these problems that Lily mentioned, and we tried several times to make, because really, as Lily said, we wanted to make use of that data from that corridor, considering that the adaptive did not work on it, and we wanted to show at least that this can have the potential to work, this type of system. Given that we were not able, after trial and several months, a couple of months, we were also considering from the beginning another corridor in Miami, which is the Northwest 119th Street. That is a 2-mile segment between Northwest 32nd Avenue and Northwest 7th Avenue that contain 9 signalized intersections. Very busy corridor. They have installed actually now an adaptive signal control system, and we evaluated that for the FDOT District 6. It has high resolution control data and travel time from here, as well as data from Bluetooth readers. We use the Northwest 119th Street as our case study for the remaining of this project, and we focused on the AM peak period. Another thing that was important to us is the detector location. They had several of the links had what they call exit detectors, which are basically can give good counts. A lot of times, some with these detectors on some of those corridors, they don't have exit detectors or advanced detectors, and you don't have a good kind of estimate of the actual demand. Rather, you get either the capacity or you get volumes that are not very accurate depending on the configuration of the detectors. So as I mentioned, we use k-means clustering to identify 3 traffic patterns for use in signal timing optimization. The 3 traffic patterns clearly, when we examine them, represent relatively low, medium, and heavy volumes. However, further examination of the clusters, and then we optimize the signal timing for these signature days for these clusters. And we found that there's very small variation in the signal timing plans. When you look at the signature days, the traffic seems to be a little bit different, but not to justify using 2 different signal timing plans. So we decided eventually to merge 2 of the 3 clusters, and we ended up with only 2 clusters. In terms of the prediction algorithm, as I mentioned, we use 6 different or 7 different machine learning algorithm for short-term prediction of the traffic state for the next 30 minutes. And the prediction is to predict what cluster we're going to have in the next 30 minutes based on what we see now, what we're going or the past 30 minutes, what we're going to see in the next 30 minutes in terms of a cluster. This prediction in real-time operation can be used to activate the signal timing plans. And as mentioned, the artificial neural network algorithm predicted the best results in terms of accuracy and area under the curve and other performance measures of machine learning performance that is standard used in assessing those algorithms. Does this study use the AI prediction model in the remaining tasks? And this table shows the comparison between the different measures of performance that are, as I mentioned, standard machine learning measures between the 7 different algorithms. And you could see that we compare that these 3 sets. One of them is you use the data between 7 to 7:30 to predict the next 7:30 to 8. And as the morning peak progress, we have now more data. So now we have 7 to 8 a.m. data, and we can predict 8 to 8:30. As we progress, we have data from 7 to 8:30, and we can predict 8:30 to 9. So we train the machine learning to predict the cluster based on this, whatever data we have prior to, in the peak prior to the period that we are predicting. We found out that yes, as time goes by and we have longer period of time to use in the prediction, the accuracy start increasing and the performance start improving. However, we still see that they perform relatively well, even with half an hour in the peak, in the beginning of the peak period. So now I think, Lily, you want to start talking about this, guys? I think, this is mine still, is that right?
Yes.
Sorry about that. So we evaluated 10 days, we selected 10 days randomly to be used in the evaluation. And as I mentioned, so those 10 days, we said, okay, what if those 10 days have used different type of signal control strategies? Would they improve with the performance-based TRPS. And given that we found that, as I mentioned before, cluster 2 and cluster 3 were close to each other, we merged those two together. And then the prediction algorithm we found could accurately predict the traffic cluster for 8 out of the 10 days. So it determined what is the cluster for 8 of the 10 days. But we found out that the remaining 2 days were days that are actually on the boundary between the two clusters. That means that whatever plan from both of them, from both the clusters, whatever signal time plan optimized from each of those would have worked well anyway. So it was not a big problem in that case, that there was misclassification of those 2 days in terms of what cluster they belong to, because they are on the boundary. You could see here that there are different days, and as I mentioned, 8 of the 10 days are true. But the evaluation of the control alternatives, we have 5 different control alternatives. So the first one is the base condition that currently used by the signal agency in the system. Actually, before they implement the adaptive, not currently, but that is the signal control before they implemented the adaptive signal control. Plan 2 is to optimize the signal timing based on signature days of the true clusters. That means these plans are the ones that for perfect prediction. If you predict all the 10 days correctly, 100%, then this is what you're going to get. And that theoretically, that is the ideal situation. Alternative 3 is to optimize the signal timing based on the signature day of the predicted clusters. So that means that for the 2 days that happen to be misclassified, we implement the wrong kind of, quote unquote, the wrong plan for those to see what is the impact of not predicting right in all cases. For alternative 4, we optimize the signal timing for the signature day of the entire database. And that means, okay, what if we just use clustering and just obtain a signature day for the whole based on continuous data, and then use that in the optimization, and don't worry about clustering and prediction and so on, but has a better day for the optimization than what is normally used. Use the whole kind of long period, couple of months, 3 months data or a year data to select the signature day. For 5 is to optimize the signal timing for a random day, and that is supposed to show that sometimes agency go to the field, the consultant or the contractor go to the field in a random day in the month, and then select a day and use that in the optimization. So those are the 5 alternatives that we can compare. I think now, Lily, this is yours. Sorry about that.
Sure. So what we did then is we used the highway capacity software 7 version, which also includes the Transit 7F signal control optimization, which has the genetic algorithms as part of it. So Transit 7F is now part of ATS. So we optimized, actually that's the work that Ehsan Amini did for from the UF side, and optimized using the ATS software all the scenarios that Mohammed mentioned earlier to run it within the highway capacity software. One of the questions that we've had is, should we then go forward with a simulation evaluation as well? But this is something we haven't done yet, but we're considering doing as a next step. Mohammed, back to you.
Okay, so then we have the evaluation results for different scenarios, and then for every day we look at different alternatives performance. And in general, what we found out based on the results is that the TRPS is performing better than the other alternatives by a certain percentage, which I'm going to show in the next slide, that it has potential to be implemented. There are potential for improvement, which I'm also going to mention in the conclusions and the recommendations. So in conclusion, the data quality and detection configurations are critical. As Lily said, data quality proved to be a problem in one of the case studies. Also detection, you would want to have the configuration of detection in a certain way to give you at least some points to detect the patterns in the traffic and the volume, and in addition to the other measures like the green occupancy ratios and on critical movement and so on. The results of the case study showed that the performance-based and predictive TRPS method can decrease the travel time by 7% compared to existing traffic signal system. By the way, these, as Lily said, these are based on highway capacity software evaluation, and I'm going to mention in the next slide some future work. So 7% compared to existing traffic signal timing, 4% compared to optimized signal timing based on the entire data set rather than cluster and activation, and 17% compared to a practice where the agency goes to the field and collect the data for a random day and instead of having a longer period of time based on automated data sources like the ATSPM that give the variation in traffic pattern throughout the year. This shows that the TRPS based on traffic pattern identification and prediction has the potential of improving traffic performance compared to the other assessed alternatives. It's the recommendation. It's recommended that the TRPS is implemented for testing in real-world environment to prove the concept based on real-world deployment. As Lily said, the simulation-based evaluation is recommended. However, sometimes through the years, as many of us as researchers know, sometimes when the signal timing, not only researchers, practitioners also, when simulation, signals are optimized using a certain tool, their assessment using simulation can be have a problem, and especially when the difference is like 5, 7, 8% because of the difference in how they model the traffic flow. So a lot of time what you want to do is to optimize using or select your signal control using a tool and optimize it using a tool, and then evaluate it using hopefully a similar tool at least, or same tool. So for example, you could use simulation-based optimization, and then you use simulation-based evaluation in that case. The signature day was selected in this study as the day that is closest to the other days in the cluster. And we think that there may be other ways to select the signature day that may produce even better results. For example, we could evaluate that versus selecting maybe a day that has higher volume than the rest of the days in the cluster by, let's say, maybe the 85th percentile day or something like that. And instead of having a day that is the closest to all the other days in the data set. That would be interesting to compare in hopefully a future study on the subject. So now we have a question and answers, and
machine learning algorithms used for clustering are considered unsupervised algorithms, aren't they?
Yes, clustering normally considered unsupervised, while the predictive are considered supervised. I mean, predictive, the predictive that we use are considered as supervised learning.
Great. Our next question is, as a general comment, simulation can also be used to generate the training data in addition to evaluation.
That's a great point. We have done this many times in the past to use simulation to generate. Obviously, in those cases, what you want to do is to be 100% sure that your system, if you do it for practical use, I mean, if for research you can do it, but a little bit with less caution. But especially if you are doing it for practical use, you need to calibrate those simulation models to reflect the real world data perfectly in terms of the green actuation, the green occupancy ratio, so it's not like your typical calibration based on travel time and speeds and volume, but you have to look at it on an intersection per intersection basis. Once you have that, and you have that variation in those fine-grained performance metrics through the year, kind of be sure that they reflect those somehow, then you could, so at one point in time, that could be a good thing to look at. If that can be done, it can be done. I mean, it is ideal, and we've done that in the past on a different project. Also, Stride project, by the way, we did that because we didn't have good field data at that point in time, and we trained the model. I think that was for incident-based. We wanted to look at signal timing plan to activate for incident-based conditions using also machine learning. Was a project that we also done about 2 years ago for Stride.
I just want to make a quick comment here. Often we do our experiments in simulation. People ask, couldn't you do this with field data? This is one of the few cases where we get the inverse.
Yeah, that's very good, Lily. That's very good point. You know, we know, is that right, that sometimes simulation is powerful and we do it, but the reviewers sometimes they love real world data, and anything that is not real world data, they question it. So that's, yeah. I've seen that many times. Yeah.
Right, and I think that the field data are always a better approach whenever you can get it, because you get a better sense of the variability. It's really difficult to replicate the variability that we have in the field, especially when you're looking at the full year in simulation.
Yes, yeah, right.
Excellent. We have another question. We'll go back to our first one, and Dr. Amini is on, and he's going to answer that. Are the TRPS plans all fixed time or actuated coordinated?
Hello everyone, it's Ehsan Amini, and yeah, we did that part. So they're all, I believe it was actuated coordinated signals, like all the signals over that corridor. As we had the same in the like current situation, we have like actuated coordinated signals over that corridor. So
yeah,
we optimize for the same thing.
Yes, and that's a good question, and good. Obviously, thank you, Ehsan, for the answer. And that's another reason that maybe, you know, a simulation-based optimization would have even been better. So that even increased the difference between the high capacity software optimization and the simulation of the actuated signals, because they consider the actuated signal differently. While if you have an optimization routine that runs with the simulation somehow, that could take care of that, and you are really doing the optimization based on how the simulation think that the actuated controller work.
I don't see any more questions at this time. So at this point, we'd like to thank you so much for participating in today's STRIDE webinar, and we hope to see you in future webinars. I'd like to thank both of our speakers today very much for a great webinar, and to our attendees for their questions.
Thank you.
Thanks, everyone. Bye-bye.
Bye-bye.